introduction. And good morning, everyone. My name is Juhee from KAIS. Today I'll be presenting the work titled with Hot Microtube Flowmetry with Heater Integrated Microchannel Resonators. Precise analysis of leakage in microfluidic system is becoming more and more important as level on chip and device miniaturization is developed. For example, in biomedical applications, microfluidics allows for advance of on-chip analysis, helping to simulate complex biological environments. In chemicals, microreactor is one representative example which enables control of chemical reactions on a small scale, increasing efficiency and reducing sample waste. In electronics, for example, microfluidic cooling systems are used to efficiently cool chips, which is important for maintaining performance of chips. Across all these fields, accurate measurement of flow in microfluidics is important for process control and device performance. For microscale flow measurement, three technologies are commonly used: ultrasonic, Coriolis, and thermal mass flowmeters like hot oil anemometers. First, ultrasonic flowmeter use ultrasonic waves transmitted through the fluid to measure the travel time difference. This method provides intuitive and direct velocity measurement. However, it has limited in minimizing their physical size due to the transducers. Coriolis flowmeters can measure flow rate and mass density separately. The liquid flows affects the torsional force on a vibrating tube, while a change in the vibrating tube's frequency is related to the density. However, Coriolis flowmeters have low resolution at low flow rates, especially with low Reynolds numbers, due to the minimal torsional force generated. In addition, although there have been attempts to fabricate a mass-based Coriolis flowmeter, it is yet limited to the size larger than 3 mm. Thermal mass flowmeters are operated by electrical heating of a tiny wire inside the flow stream, measure a cooling effect of the flow on the wire. They have drawn attention due to their high spatial resolution down to microscale characteristic length and maintaining high accuracy at low Reynolds number even with gas flow measurement. Still, application in liquid flow measurement within microchannels is somewhat limited owing to a dependency of fluid properties on measurement and the difficulty of integrating fragile structures into liquid flowing channels. Our platform, the Heater Integrated Microchannel Resonator, hereafter HMR, combines resistive thermometry and resonance densitometry. When the liquid is stationary, not flowing, resistive thermometry allows us to measure the thermophysical properties of the liquid inside, such as thermal conductivity and specific heat. When the liquid is flowing inside the microchannel, we can measure the flow velocity by analyzing the cooling effect of the moving fluid. Our multimodal platform is a tool that integrates the advantages of both thermal mass flowmeters and Coriolis flowmeters. Unlike conventional thermal mass flowmeters, which cannot decouple the effect of thermophysical properties from flow measurements, our system can analyze both aspects simultaneously. In this slide, I will explain the basic structure of HMR. The liquid sample enters the microchannel, where we employ Joule heating and resistive thermometry for applying heat and simultaneous temperature measurement and resonance densitometry to measure fluid properties such as density. The polysilicon layer is deposited on the insulating layer, and the suspended channel is fabricated by the LPCVD silicon nitride with the sacrificial polysilicon etching process. Here is the SEM image of HMR, which clearly shows the blue pseudo-colored liquid channel and the red colored integrated heater. The graph shows the result of temperature calibration with micro-Raman thermometry by using temperature-dependent Raman peaks of silicon, which is used as a heating electrode under the microchannel. And afterwards, electrical resistance is used as a temperature sensor by this calibration. This is the experimental setup we used. The setup can be divided into several main parts. First is to minimize the thermal and mechanical energy loss. We construct the vacuum chamber and connect it with pump for environmental control. It has optical window for resonance monitoring and fluid port for liquid delivery, and electrical readout for resistance monitoring. First, microchannel is heating with a waveform generator and measure the resistance changes via data acquisition system. The HMR is connected through pogo pins for electrical connection. The resonance shift is measured using a laser and a polarizing beam splitter and segmented photodetector. A login amplifier and phase lock loop help track the real-time changes in resonance. Lastly, liquid samples are contained inside the pressurized vials, where flow rate can be controlled by the pressure regulator. In the thermal sensing process, by measuring the temperature response, we can infer the thermal properties of the liquid. To be specific, low thermal conductivity increases the thermal resistance through the fluidic channel, and with the same power input, steady state temperature is higher in low thermal conductivity case. In contrast, low heat capacity reduces total thermal mass, thus temperature response is faster in lower heat capacity case. While in mechanical sensing, the well-known relationship between resonance and density is used to determine the liquid density. Additionally, we can measure viscosity by analyzing the amplitude of the resonator vibration. The equations shown below are derived from dimensional analysis, and the graph below show real-time measurement of resistance, resonance frequency, and vibration amplitude obtained simultaneously. Here are the results of property measurements across different temperatures. In summary, we measured thermal conductivity from the change in resistance, specific heat capacity from the time response of the temperature, density from changes in resonance frequency, and viscosity from the vibration amplitude. As temperature changes, the physical properties of the structure also change, resulting in different calibration curves. And these graphs illustrate how we have accounted for these changes to ensure accurate measurements across a range of temperatures. And we calculated combined properties such as thermal diffusivity, kinematic viscosity, and Prandtl number. These properties help us better understand the thermal and mechanical behaviors in our sensor. Then we compare the thermal measurements in stationary mode and mobile mode, where the liquid is flowing. In stationary mode, heat transfer is driven only by conduction through the liquid channel. However, in mobile mode, in the liquid flow introduce convective cooling, which adds an extra term to the heat equation. By comparing these two modes, we can analyze how the increase in the convection coefficient caused by the flow relates to the changes in the material properties. Then we investigate how the system behaves under the different flow velocities. Let's start by focusing on the 0 millimeter per scale case, where there is no fluid flow. And as we introduce flow, the resistance changes, which reflects the difference in temperature under the same applied power. Higher flow velocities lead to greater cooling as the moving fluid removes heat more efficiently, resulting in lower resistance. By analyzing the difference in resistance at various flow velocities, we can quantify the heat transfer enhancement by fluid flow in the microchannel. On the left, we used the well-known equation King's law, which is typically applied in gas flow measurement to fit the temperature data. As the velocity increases, the temperature difference decreases. This is because the convective heat transfer becomes more dominant with higher flow velocities, enhancing the cooling effect. And on the right, we calculate the heat transfer coefficient based on the input power Q and heat exchange surface area A and the measured temperature difference, delta T. And this experiment is repeated with another liquid sample, glycerol water mixture. And we observed that glycerol water mixture show a higher temperature compared to the pure water at the same velocity and the same heating power. And this is because glycerol has lower thermal conductivity and heat capacity, resulting in a reduced cooling effect compared to water. And here is conclusion of our study. We propose hot microtube flowmetry using a heater integrated microchannel resonator. And integrated thermal and mechanical sensing measure flow speed of liquid as well as liquid properties. By comparing stationary and flowing liquid, we showed how liquid flow affects the convective heat transfer. And that is all for my presentation, and thank you for your listening.